All right, we're going to do a little video here on the idea of the multiplication rule and independence of events. All right. So let's recall, remember we said probability is always a value between 0 and 1, including 0 and including 1. I'm not sure if I mentioned that before, but we want to notice that a probability of 0, if you see something, you're told the probability of event A is 0, that means event A can never happen. It's never, ever going to happen. Now, I used to use the Cubs winning a World Series as an example of this, but was it 2016? They finally did win a World Series, so I can't use that anymore. But you get the idea. Probability of 0 means something can never happen. So sort of like rolling one die and getting a 13, right? Can't happen. That's a probability of 0. Probability of 1 means something is certain to happen, absolutely certain to happen. So if you had a die where all 6 sides were the number 6, roll that die, the probability of getting a 6 is certain. It's a 1, okay? And anything in between, right? The closer to 1, the more likely the outcome, the closer to 0, the less likely the outcome. So we want to get into something called the multiplication rule. Remember, we talked about intersections. This involves intersections of 2 events. So when we say the intersection of 2 events, A and B, so we're going to let A and B be 2 events, okay, any 2 events. If A and B are called independent events means that one outcome has no effect on the other, right? Now, you can take a philosophy class and we can argue that everything we do in life has an effect on every other thing we do, but that's a different class. We're talking about probability here. We're going to call things like let's say I flip a fair coin and I roll a fair die. The heads or tails on the coin has no effect on the number on the die. That's called an independent effect, an independent event, or 2 events. One has no effect on the other. So if that's true, we say they're independent, and the probability that they both happen, the intersection of those 2 events, is simply the product or multiplying the 2 individual probabilities. That is the multiplication rule right there. If 2 events are independent, then the probability that they both happen is just the product of their 2 individual probabilities. So again, think of flipping a coin, 1/2 and 1/2 for tails, so probability of heads is 1/2. Probability of rolling a 2 on the die is 1 out of 6. So the probability of flipping a coin, getting heads, and rolling a die and getting 2 is 1/2 times 1/6, or 1/12. Okay? That's the multiplication rule. Now, of course, 2 events are not always going to be independent. If they're not independent, then we bring into the equation the conditional probability that we spoke of in the intro to probability video last time. If A and B are not independent, and we want the probability of their intersection, that they both happen. So the probability of A and B happening is going to be the probability that the first event happens times the probability that the second event happens, given that the first event has already happened. Now realize, let's take this a little deeper. This conditional probability, if the events are independent, well, the condition here makes no difference if they're independent. The probability of B happening given A, well, who the hell cares if A happened or not? If they're independent, A has no effect on B. So if A and B are independent, that conditional probability right here is just the probability of B, and we're back to where we were if the events were independent. So these 2 equations give you the probability of the intersection of 2 events, whether they're independent or they're not. Now, what I want you to notice here, and this is really a very helpful bit of knowledge that I find a lot of students don't see for some reason, but realize here that the probability of A and B, well, isn't that the same as the probability of B and A? Right? If two events are happening, then two events are happening, right? We can call it the probability of A and B, or we can call it the probability of B and A. These two things represent the same outcome, events A and event B happening, both of them. So depending on what information you're given in a problem, sometimes you want to look at the intersection equation like this, but sometimes you would rather look at it like this. Notice this and this give you the same probability of these two things happening. We've just reversed the A and the B from here to here, and therefore reverse this part of the equation. The first event happening, B, times the probability that the second event happens, given that that first one already happened. So for the intersection of A and B, we can use this equation, or we can use this equation. It's a very important bit of knowledge to remember. Now, from these equations that we just looked at for the intersection, we can solve this equation for the conditional and come up with an equation for the conditional here. I'm just taking this equation here and dividing both sides by the probability of A. Just like any algebraic equation, if I divide this side by the probability of A, I'm left with that condition. And then this side also has to be divided by this, and that's where we're getting this. All right, so the conditional probability of event B happening given event A happening, we can use this formula. Sometimes we'll be given information that makes this formula more useful to us. Sometimes we'll be given information where we want to reverse it. A and B, B and A, same thing, right? Two events, A and B happening. Two events, B and A happening. The only thing is we come up with a slightly different formulation on this side because here B is first, here A is first. So now it's the probability of the first event happening times the probability that the second event happens, given that the first happened. And just like I did here, using this equation, I can now solve this equation for the conditional and come up with this. So these are two different equations, this one and this one. This is the probability of event B happening given that event A already happened. And this is the opposite or the reverse, the probability of A happening given that B already happened. Okay, so these are conditionals. Sometimes you'll be given two of these three values, so you want to use this equation. Sometimes you'll be given two of these three values. So this would be the more useful equation. But realize they both derive from the multiplication rule and independence of events. Two events are independent, multiplication rule. Not independent, that introduces the conditional. This equation is the same as this equation. From this or this, we come up with equations for the condition. Right? So this is going a little long, so I'm going to do mutual exclusivity and the addition rule in a separate video. That'll be our next video. So this video, I just want to cover the multiplication rule and independence. We'll go through a couple examples on the screen here. If you're asked to prove that A and B are independent, if you can show that the probability of their intersection is the product of their two individual probabilities, then you have shown that they are independent. And similarly, if we're told that A and B are independent, we can immediately go to that multiplication rule and know that that's going to be true. All right, so let's look at a couple simple examples here on the screen. I'm going to share my screen here so that we can see what's going on. All right, get rid of this. All right, so these are just some old tests from old classes. And this is just a general example of probability. So let's look here at the question first. If we say we have a sample of 317 MP3 music players, 19 were defective. How would we estimate the probability that a new player is defective? Well, this is just simple relative frequency. 19 are defective out of 317. So that's going to be our probability. 19 out of 317. If we change it to a decimal, it's going to go to this number here. Okay. What is your estimate for the probability that a new MP3 player is not defective? Well, if there's 19 that are defective, that means 298 are not defective. So 298 out of 317. Or we can look at, I don't know if we mentioned the complement before, but a complement is everything other than an event. There's only two outcomes here, right? The MP3 player is either defective or it isn't. So there's only two outcomes. So the probability that it's defective, we said, was this number. So the probability that it's not defective is just the total probability of 1. And a sample space is always, the probabilities of all the values in a sample space are always going to add to 1 because it has to be, the outcome has to be something in the sample space. So we can just subtract this probability from 1 to get the probability that it's not defective. And like we said, the sample space here, there's only two outcomes. It's defective or it isn't. Notice that these two probabilities add up to the total probability of 1. And that's always going to happen. All right, so that's just relative frequency. Now let's go to one here that involves, let's go to number 4 here. Let's go to number 5. This involves the independence rule, multiplication. So here Robert is applying for a bank loan to open up a pizza. You can read it yourself here. The important things is to record the information, all right? And label your events. We used A's and B's. Those are generally the easiest letters to use. You can use anything you want, but let's record the information and then we can set up the equation. So past records show the probability of being approved on the written application is 0.63. So we'll call being approved on the written application, we'll call that event A. Probability of event A is 0.63. Probability of being approved by the interview committee is 0.85, given that the candidate has been approved on the written application. So we've already decided the written application being approved is event A. So we'll let the probability of being approved by the interview committee as event B. But this is conditional given the candidate has been approved on the written application. And the question is, what's the probability that he's approved on both? Okay, so that's an and on both. Well, now let's look and see how we set this up. So again, we want to label things. So probability of being approved on the written application, we're going to call that event A. Okay, that's event A. The probability of event A we're given is 0.63. And then we're told the probability of being approved by the interview committee, which we have labeled as event B, given event A has already happened, proved on the written application, so that's this number, probability of being approved by the interview committee, given that you've already been approved by on the written application. The question is, what's the probability that both happen? So here we're given this conditional and we're given this probability the way we've labeled it. A is the written application, B is the interview committee. So we're given that conditional, we're given this probability. All we got to do is multiply those together using the formula we just discussed. Probability of the first event happening times the probability that the second event happens, given that the first has already occurred, and we get our probability, in this case, 0.5355. All right, so that is an example of the multiplication rule. This is just a very introductory example. Obviously, I want you to read the book, go through all the examples, trying to keep these videos short. So I'm going to end this one. And there's a picture of the screen in case you want to see all that fine information that we just discussed. And we will get into the multiplication or the addition rule and mutual exclusivity next.